In the natural world, things move in periods. Days go by, years go by, seasons, weather, temperature, so many things are periodic. So being able to take the transform of a periodic function be super helpful. So that's what we're going to do today. Be able to take the Laplace transform of a periodic function. So we have a theorem to work with when we're taking the transform of a periodic function. If f of t is piecewise continuous on 0 to infinity, of exponential order, and periodic with period capital T, then the Laplace transform of f of t is going to equal 1 over 1 minus e to the negative s times t, the capital T, that's the length of the period, times the integral from 0 to capital T, so the length of the period again, e to the negative st f of t dt. So the best way to understand what's going on with this is to take a look at an example. We're going to start off, one of the things that's really helpful with periodic functions is to be able to recognize them from a graph as a periodic function, and really the graph is what just gives it away that it's a periodic function. And we'll look at figuring out the length of the period from that too. So let's take a look at an example. First thing we can do is figure out the length of the period of this example. So starting at 0, I'm up at 1 and beginning a stretch along 1. I want to go until I'm at that same position again. And I notice that that happens at 2. Since I don't have information before 0, it's kind of a good idea to look and see, well, where does it happen again? And I notice it happens again at 4. So the distance between these occurrences seems to be 2, and that is my length of the period. So t, capital T, is going to be 2. So this is a square wave, has period 2, and it fits everything I need. It's of exponential order, it's periodic, it's piecewise continuous on 0 to infinity. So I can actually write this as a piecewise function. E of t equals 1 and 0, and it's 1 from 0 up until 1, and then from 1 until 2, it's 0. And then that tells me what's happening between 0 and 2. So then outside of that, all I have to do is make a note that e of t plus 2 just looks the same as e of t. So now we use our theorem. So our theorem says that the Laplace transform of e of t is going to equal 1 over 1 minus e to the negative s times the period, so times 2, the integral from 0 to 2 of e to the negative st e of t dt. Well, the value for e of t is different from 0 to 1 than it is for 1 to 2. So I'm going to break this integral up into 2 pieces. So this is going to be 1 over 1 minus e to the negative 2s times the quantity of the integral from 0 to 1, that's where e of t takes its first value, of e to the negative st. E of t is 1 on this interval, so we'll times 1 dt, plus the integral from 1 to 2, e to the negative st times its 0 on this interval, dt. So I noticed that 0 multiplying the integral of 0 is 0, and so my second part actually goes away, so this is going to equal 1 over 1 minus e to the negative 2s, the integral from 0 to 1, e to the negative st dt. So taking this integral and evaluating it from 0 to 1, I'm going to get 1 over 1 minus e to the negative 2s times 1 minus e to the negative s over s. Now, 1 minus e to the negative 2s, this is really 1 minus e to the negative s times 1 plus e to the negative s. It's a difference of squares there. And using that and canceling out 1 minus e to the negative s from the numerator and the denominator, then I'm left with 1 over the quantity 1 plus e to the negative s times s. And that's how we take the transform of a periodic function.